Okay, so let's turn into E and power relation. And so we have the EX, and so dx EX is always equal to what? Each other, right? X square EX and goes on, right? Any differentiation gives the same pattern for this case, okay? And so this limit, or the E, is proved with the with the over 1 value, because the limit n goes to infinity value, 1 plus 1n over n produce the E, okay? Because it's the E1, right? And so this 1 is coming from the these coefficients in here, okay? And so how about the limit definition?
So one coming from which coefficient? From which one?
This one. And then this is the 1, and then this is equal to E over 1, which means that E, okay? But if I choose to define this limit with the plus 1 and x over n, which is equal to the ax, okay? And so in this case we can write the variable to represent the overture in here. But if I take a derivative, and so the dynamic cannot dependent from the this one, okay? But we can choose any other variable to represent this one. And so this is a common root or common basis for the for infinite series. Because just remember that the Fourier series is based on the sinus and cosinus, right? Just see that. And so we can define everything based on using sinus and cosinus, okay? And so how about we know that this proof is given in here. And so how can we add the dynamicity of this term? Which means that if we have any root or common root in here, just like this one, and so we can add or we can manipulate the x value here, okay? And so assume that we use E over I times x in here. If we are choosing this value, and so at each iteration or at each integral form, we have EIX, and after that dx EIX produced IEX, right? And so this square dx EIX is yield minus 1 EIX, right? And so this is the common part. Does not change in this case, right? But we have the different coefficients in here, because the I or J is the imaginary component, and so we can create the periodicity just like this one. And so if I choose this function, and then we can corresponding, or we can refer this IX is a infinite sum of the IX k over k factorial, right? This is the basic definition. And then we can expand this term is equal to 1 and IX plus I x square 2 factorial I x over 3 factorial plus blah blah blah, right? We can expand it just like this one. And so just see that we have I is over I, right? And I square gives us minus 1, right? And so I over 3 is equal to what? Minus I, right? And I4 is given to the what? To 1, right? And so in real and imaginary axis we take the I, and after that we have minus 1, and after that we have minus I, and we have the 1, right? In the real and imaginary axis we have this one. This is the first way, this is the second, third, and fourth, right? 1, 2, 3, 4. 1, 2, 3, 4, right? Okay. What about this value? I. What about this value? What about this value? What about this value? Okay. And so 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and always goes to what? It's a periodic definition, right? But always we over 1, 2, 3, 4, or at every case we have add the another root. But it always goes to the what? The returning point to the what? The 1 or I. But just see that if we increase the root number or the over number, we have always a periodicity from the what? The real to imaginary, imaginary to real, real to imaginary, imaginary to real. Okay? And so this is cyclic operation. See? And so how can we utilize this information? Why we always return to the what? To the same point. Even if we take the what? The over operation. We increase the root numbers. We increase the power of this term. But we will always to the what? The same point in here. Real to the imaginary, imaginary to the real, real to the imaginary, imaginary to the real. How can we use that?
So we have just four like roots. The main roots we have just four, and others are dependent on it. So we just need to use four roots to create any function to back to it.
Yes. Just see that the important part is that even if increasing the number of feature, root, power of function gives us periodicity in here. This is not impossible. This is possible, right? And so just continue with this one, and then we have the ix is equal to the what? 1 plus ix plus ix square 2 factorial ix over 3 factorial, and blah blah blah. Okay? And so eix is equal to the what? The 1 minus x square 2 factorial plus x4 4 factorial minus x over 6 factorial goes on, right? Because this is the real, this is the imaginary, this is the real, this is the imaginary, this is the real, this is the imaginary, and so we can decompose these terms into the what? The I times this one, imaginary one, and this is the real one, right? And so this is the x, right? And so we have also x over 3 factorial plus x over 5 factorial, x 7 factorial plus blah blah blah. Okay, this is the projection of real axis. This is the projection of imaginary axis. So, what is this? Yes, but it's a special function that we use all the time in the math. What is that? Yes, this is the cosinus. This is sinus. This is the proof of the cosinus and sinus. Okay? So, EIX is equal to the what? Cos x plus I sin x. This is the what? We call it the what? The polar coordinates. Right? So, in the polar coordinate, we can define the what? These coefficients or this projection, real and imaginary. Okay? How can we define this function in the polar coordinates? How can we create the real part and imaginary part in here? This is a cosinus and sinus, right? Okay. And so this is the case. We can draw one hypotenuse in here, right? With the coefficient of the r, right? And so what's the x in here? Yes, x, right? And so in order to represent a real part as a cosinus value in here, and so the x should be given in here, and then this is the cosinus x and this is the sinus x, right? Yes, projection of this. Okay, but how can we limit this operation? Just see that if we use the what? The some another transcendental coefficients or number in order to utilize to what? To one period in here. Just see that if we have this domination, and then we should take the what? The sum period in here. Just like this one, we have the angle in here, but this angle must be returned to the reverse value. If this is the identity, and so this must be equal to 1. This must be equal to the minus 1. How can we do that? Yes, pi. EI pi cos pi plus I sin pi. What's the value of the cos pi? Minus 1, correct. What's the value of the sinus pi? Yes, I 0. And so we can wield that I pi plus 1 is equal to the 0, which is the definition of the what? Euler identity, right? Euler identity is coming from this notion. And then if you want to complete this period, and so we can draw this circle in here, just like this one. Okay, and so at every case minus I j, and this is going to 1, and so we can build what the Euler shape or Euler geometrical representation of the what, this nomination. And so it's the proof of the cos x. The other term is the sinus x. Okay, and so we can use the angle and the magnitude to the what to create the periodic signals, because if we have this definition, and so we always return to the same point, which is independent from the time, right? And so what is this shape? We should analyze it right now. We need to understand this shape. Real and in, and so we can draw the what, these terms. Okay, firstly you should know that this is a geometrical representation, right? If this is the geometrical representation, we should utilize what? Pythagorean theorem, right? And so if we know the Pythagorean theorem, and then this is the R or unity, and so we have a right angle in here, just like this one, right? Okay, and so how can we use this term if the unit basis or it's equal to the 1, and so the magnitude of this term is equal to the what? This is cos x and sin x. And then if this is true, if this is the polar coordinate, and then we have this nomination, and so absolute value of this function must be equal to the what? To the 1. And so this is the 1 square, r is equal to the 1, and so sin square x cos square x must be equal to the 1, right? This is the proof of what? Sinus square plus cosinus square must be equal to what? 1. It's coming from the what? The Euler identity. This was provided. See? It's the geometrical identity for the what? For our nominations. But just see that in order to build or use the J, we should say all the time delta S must be equal to 0, right? Because we can change the what, the T and X just like this one in sinus or cosinus, right? But we don't have any change in this R value or the hypotenuse value, and so it's a perfect what? Perfect circle, right? Because we use the pi. The pi creates the what? Perfect circle, right? And so if we don't change the value of the hypotenuse in the Pythagorean triangle, and then we can convert the time to the frequency, because we convert the real part to the imaginary one based on this equation. See? Because at this point and at this point just we have the imaginary part without breaking the what? The geometrical representation, right? And always we have this nomination 1 I minus 1 and minus I, right? And so at over and over and over, taking the power of the what? This term, 1 over 0, 1 over 1, I over 2, I over 3, I over 4, I over 5. If we increase the over number, we get the same point. And so if we are using the what? The infinite roots in here. We can define it with the what? 4 roots with periodicity, right? Because we know that at each 4 power we return to the same point. It's a huge utilization, huge basis to define what? Infinite roots, because we don't have to look at the what? Every root at the infinite domain. We just always seek to what? The 4 roots. Just now. See? And so, which we can say that this is called frequency. And so, frequency is the what in geometrical representation to this one. It's the physical interpretation of the what? Frequency. Any question? You get it? Hakan? You're talking right now. Any question? Any? Better? You? You see that? We just use the Pythagorean theorem. And so, if we keep to what? The Pythagorean hypotenuse as a constant, and then we can convert the whole energy into the another one. And so, at each over operation or the power operation, if we increase the number of the over, and so we just return to the same point, which we call it the frequency. Just remember the control theory lesson. We always translate the system into the what? Into the frequency one. Why? Yes, we evaluate all the system, which is time dependent. We need to convert this system into the frequency domain or frequency one. Why? No. Why? If we convert everything into the frequency domain, and so we can treat this system as an algebraic equation. For example, 1 divided by s squared plus 3s plus 2, right? And so we can say that this system is stable or not. Or we can guess, or we can find the last value of this system, independent of the time. Why? Because we have periodicity in the frequency domain. And so we don't need to evaluate the whole roots in time. Just see the frequency in order to understand that the system is stable or not. Okay? And so this shape, this Euler identity shape, is the what? Is the unit circle, but unit frequency. The frequency definition is given or is built based on this termination. This is the exact definition of the frequency. Frequency means that if we start in the 1 and then if we are taking over this nomination in here, x, 1, 2, 3, this is a power term. If we increase the 4 in this case, and then we return to the 1. E, I, I0, I1, I2, and I3 creates the what? The basis frequency. In E domain, the reverse E preserve to energy conversion. Okay? If you select this, if you take the derivative, and always we get what? The I1, I2, and I3, right? See that? Because the cosinus and sinus are produced based on this definition right now. Otherwise, we cannot define the cosinus and sinus, right? And so, this is why we can use the cosinus and sinus in the Fourier series to represent what? To represent any function. Any continuous or discontinuous function, because we have the infinite roots in here. But with what? With this Euler shape. Okay? Do you understand that this concept? The graphical shape of the frequency is the what? Is this circle. Why? We can take the overturn in here, and then if we take the 0, 1, 2, 3, and always we go to the what? The same point. We return to the same point at each case.
Yani hocam demek istiyorsunuz ki biz dünyadaki her şeyi doğru frekansla bulursak birbirine dönüştürebiliriz.
Yes, but with one condition: the hypotenuse of the Pythagorean theorem is constant.
Bu da yani hypotenuse teoremi sayesinde bunu kanıtlayamıyor.
Yes, because if you don't have this notion, if we R must be equal to the C all the time, and then we can convert the every energy to the another one. Just like potential kinetic energy, right?
Böyle bir şey yapamaz. Enerjinin içindeki şeyleri de yakalayabilir yani.
Yes. It's beautiful, right? See? Okay.